In the previous sections, we have seen how the principle of linear superposition leads to constructive and destructive interference and explains diffraction. To this point, we have only considered waves of the same frequency. We will see in this section that two overlapping waves with slightly different frequencies leads to a phenomenon known as beats. However, linear superposition is still the principle that gives rise to this effect. Let's consider sound waves being created by a tuning fork. This is a device that, when given a sharp blow, usually with a hard rubber mallet, will vibrate and produce a sound wave of a single frequency. The figure shows sound waves coming from two tuning forks sitting side by side. The frequency of one of the tuning forks is 444 Hz, and the frequency of the other one is 448 Hz. Let's listen to each of the two tuning forks individually. First, the sound at 444 Hz. You hear a clean, crisp, and constant tone. Now let's listen to the sound at 448 Hz. Again, you hear a clean, crisp, and constant tone. Since the frequencies of the two sound waves are quite close to each other, you may not have been able to hear any appreciable difference in the pitch of the sound. Now we want to activate both tuning forks simultaneously. Something very cool happens. Listen again. You should have heard the loudness of the sound rise and fall periodically, faint then loud, and so on. These periodic variations in the intensity of the sound are called beats, and they result from the interference of two sound waves with slightly different frequencies. The figure shows the condensations and rarefactions of the sound waves separately. In reality, however, the waves spread out and overlap. In accord with the principle of linear superposition, our ears detect the combined total of the two sound waves. Notice that there are places where the waves interfere constructively and places where they interfere destructively. When a region of constructive interference reaches the ear, a loud sound is heard. When a region of destructive interference arrives, the sound intensity drops to zero, assuming each of the waves has the same amplitude. The number of times per second that the loudness rises and falls is the beat frequency, and it is the difference between the two sound frequencies. Therefore, in our example, you should hear the sound loudness rise and fall at a rate of 4 times per second, or 448 Hz minus 444 Hz. Let's listen to these two frequencies again. You should be able to hear the 4 Hz beat frequency. The following figure helps to explain why the beat frequency is the difference between the two. In the figure, we show two individual sound waves in blue with frequencies of 10 Hz and 12 Hz. We choose these low frequencies just for convenience, even though they lie outside the audible sound range, but audible sound waves behave in exactly the same way. The top two drawings show the pressure variations during a 1-second interval of each wave. The third wave below them in red shows the result of adding the two blue sound waves together in accord with the principle of linear superposition. Notice the amplitude of the red sound wave is not constant, but varies from a minimum, or faint sound, to a maximum, or loud sound, back to a minimum, and so on. Two loud faint cycles, or beats, occur in the 1-second interval shown in the drawing, which corresponds to a beat frequency of 2 Hz, which is just the difference in frequencies between the two sound waves, or 12 Hz minus 10 Hz.